Hello and welcome to this lecture. This is basically third lecture of this module, and in this lecture we will be discussing about hypothesis testing. You know that in the last lecture we actually continued that hypothesis testing. We started that one. So, in this lecture we will continue the same the hypothesis regarding one mean or concerning one mean. So, one mean means here we are having one sample. So, we will do some testing. Basically, this hypothesis testing are drawing some inference probabilistically from the sample mean with respect to the population mean, those we discussed in this last lecture. So, our outline for today's lecture is hypothesis concerning one mean, hypothesis concerning two means, hypothesis concerning one variance, and hypothesis concerning two variance. And if time permits, we will also see the probability paper that we are talking about, that once the data is available. Generally, so far what we have done, we have assumed that it is following some particular distribution. So, this probability paper is basically that first step for a graphical inspection of to test that what the data possibly could follow. So, this is basically the test of the sample data, that what is the distribution that population may follow. So, that if the time permits, after this hypothesis testing we will do that one also. Well, so hypothesis concerning one mean, let us consider a population with mean mu. A sample size n is selected randomly from the population. It is to be tested whether this mu is equals to mu naught or not. So, this mu naught is basically one threshold value that we need to test whether from the sample whatever the mean that we are estimating from this estimation technique that we discussed earlier, whether that is having some relationship, so that whether probabilistically we can infer something about its some specific value. So, that specific value is your mu naught, what is our test, what is our goal to test this population mean. So, here the test. So, you know that from our last lecture we have to define some test statistics. So, here the statistics is that z equals to x bar minus mu naught divided by sigma by square root n. This sigma by square root n, that you know that is the standard deviation for the sampling distribution of this mean, and this x bar is your mean, and this mu naught is the value which we are expecting that population mean might be this mu naught. So, here you know that this is a reduced standard variate now. So, this z is a random variable which is following the standard normal distribution. And the critical regions for testing this single mean, and again here the assumption is that the population is normal and it is a large sample. This large means here you can say that approximately if the sample size is more than 30, we can consider that this is a large sample. So, this critical region at the significance level alpha, and the discussion on the significance level also we have covered in this last lecture. So, if there are two possible cases, it can be one sided or it can be two sided. For this one sided, it can be the left hand side or the right hand side, and reject the null hypothesis if this z is less than minus z alpha. In this case, when the alternative hypothesis is mu is greater than mu naught, then z is greater than z alpha. And if it is a two sided testing, mu is not equal to mu naught, then whether z is less than minus z alpha by 2 or z is greater than z alpha by 2. And you know that this z alpha by 2 is the quantile for which that remaining probability is your alpha by t towards the right hand side of this one that we have discussed while discussing that critical zone. So, if that test statistics falls in this critical zone, then we have to reject the null hypothesis. So, let us consider a normal population with the mean mu. The population variance sigma square is unknown. A small sample n is selected randomly from this population. Now, in this case what we are doing so far, what we are telling that if this sample is large, now we are discussing if the sample is small, and as I was telling that if the sample size is less than 30, then we have to consider that this is a small sample. And here if that the statistics for this null hypothesis and the alternative hypothesis, if we consider it to be this central one, or in fact it is not only for the central, it can be one sided also. So this quantity now which we were just estimating as a z value that we have seen, now this s is replaced has replaced that sigma. So sigma by square root n, that sigma was the standard deviation for the population. Here it is a small sample, so we don't, and the variance is unknown, population variance is unknown. So we have to estimate again this one from the sample. So this s is basically the standard deviation estimated from this sample. And so this quantile now is a random variable having t distribution with n minus 1 degrees of freedom. And for this case the critical regions will be, for this one sided test, it will be t less than equals to minus t alpha, and if it is right hand side then it is t greater than t alpha, and for the central test it is less than minus t alpha by 2 or greater than t alpha by 2. So now you can see that for the large sample we are approximating it with the standard normal distribution, and if it is a small sample we have to approximate it to the t distribution with the degrees of freedom n minus 1, where n is the sample size. We will take up one problem here. The problem states the specifications for a certain construction project require the steel rods having a mean breaking strength of 4000 kg per centimeter square. If 6 steel specimens selected at random have a mean breaking strength of 3750 kg per centimeter square with a standard deviation of 200 kg per centimeter square, test whether the mean breaking strength is below 4000 kg per centimeter square at the 0.01 level of significance. Assume that the population distribution is normal. So you see that one small sample, which is sample size is 6, and it is showing that mean strength is 3750, which numerically if we test that it is below this 4000 kg per centimeter square, but is this a difference, or whether should we consider that yes, that's whatever the specimens that is being supplied for that project is really less than the specification. So that statistically we have to infer about that. So here the sample size is small and this population variance is unknown, and the sample is drawn from a normal population. So the stress statistics, as we have discussed so far, is that t equals to x bar minus mu naught divided by s by square root of n, which is following a t distribution with n minus 1, n is equals to 6 here. So 5 degrees of freedom. So our null hypothesis is whether this is greater than or equal to this 4000 kg per centimeter square, which is our specification. So we have to test that whether it is below that our specification. So that is why in the alternative hypothesis we put that mu is less than 4000 kg per centimeter square, and this alpha is equals to 1.01. So the criteria here is that, as you know, it depends on this what is the level of significance. So this t 0 alpha, and it is a one sided test. So this t 0 alpha for 5 degrees of freedom from the standard table, from the standard textbook, if you see, it is 3.365. So that stress statistics, if it is greater than this, then we have to reject the null hypothesis. If we calculate this one, then we see that so this is t is less than minus 3.365. So this test statistics now from the data that is available, x bar is 3750 and s equals to 200, we are getting that it is minus 3.06. So as this minus 3.06 is greater than this minus 3.365, so the null hypothesis cannot be rejected at the significance level of 0.01. So we cannot claim, we cannot we are failed to prove that this mean is really less than the specification, which is 4000 kg per centimeter square, even though the mean that we have seen for the 6 specimen is 3750. Well, now we will take that hypothesis concerning 2 means. Now this 2 means there are 2 samples are there and 2 sample means are there. So we can test whether many questions we can ask that whether both the sample is having the same mean, even though that so far the sample means should not be exactly same. that we can test, and then we can test that whether the one is really greater than the other one, that also we can test. So here what we are taking is that basically the difference between these two means, that is the x1 is the mean for the first population and the x2 is the mean for the second population. So if we take this difference, then the mean basically now it is becoming a single random variable with that delta value. Now if I put the delta equals to 0, that means both the means are effectively what we are testing, whether the means are same or not, or depending on what value of this delta that we are selecting, depending on the whether we are testing that whether x1 the mean for the first population is greater than the second population, and so on. And this sigma, this denominator sigma x bar minus x2 bar is the standard deviation for this difference. And you know that this z is now the random variable which is following again the standard normal distribution, in case that this both this n1 and n2, which is the sample size, are large enough. You can say that if it is greater than 30, then we can say that it is a standard normal distribution. So once we get this one, we can infer about this about their sample means. So the test statistics here can be that this one, this x1 bar minus x2 bar minus delta, and that standard deviation that we are getting for this difference is basically a sigma 1 square by n1 plus sigma 2 square by n2 and their whole square root, which is giving you this estimate for this standard deviation for this difference. And for the large samples, as I was telling, that if they are greater than this 30, then also we can say that this can be easily replaced by their sample standard deviation, which is again that standard normal distribution, we can say. This is for this large sample as we have shown, and then after this one we will also see that if it is a small sample. Now, so far as this is large sample, this will follow a standard normal distribution, and the critical regions are now same for this. These are the different alternative hypotheses, whether it is whether now this case is basically showing that whether this mu1 is less than mu2, and this is showing that whether mu1 is greater than mu2, and this is a two-sided test whether mu1 is not equal to mu2. So these are the critical regions as the same that we discussed earlier for the single sample mean a few slides before. And the second thing is the okay, first we will take one problem on this if the sample size is large. So a sample n1 is equals to 40 rods made of the certain alloy steel has mean strength of 4400 kg per centimeter square with a standard deviation of 450 kg per centimeter square. Another sample n2 equals to 40 rods having of this different kind of alloy steel, which is having a mean strength of 4200 kg per centimeter square with a standard deviation of 650 kg per centimeter square. Can it be claimed that the first kind of alloy is superior in terms of the strength at 0.05 level of significance? So the numerically, if I just take this mean, then I can say that this 4400 is greater than 4200, but if we see that they are spread, their standard deviation, they are so this is 450 and here it is 650. So the statistically we have to test whether really that first alloy steel is superior than the second one. So here the null hypothesis is that whether mu1 minus mu2 is less than 0. Here we have placed this delta equals to 0. And this alternative hypothesis, basically what we are testing is this mu1 minus mu2 is greater than 0. That means we are testing whether mu1 is greater than mu2 or not, and the significance level is 0.05. The test statistic, the criteria here, it should be at 0.05. You know that this Z quantile is 1.645 at 95% probability level. For the standard normal distribution, the value is 1.645. So this is our critical value, and greater than this value, if we get that Z, then we should reject the null hypothesis. So this is the value of this Z at 0.05, you know. So this Z now, if we just use those the sample statistics, and we will get that is 1.6. So which is 1.6 is less than 1.645. So the null hypothesis cannot be rejected at 0.05 level of significance. So we cannot say that whether the sample 1 is really superior than the sample 2, because we have seen that we failed to reject the null hypothesis. As I was mentioned earlier also, we should not say that null hypothesis is accepted. We should say that either the null hypothesis is rejected or it cannot be rejected with the sample data, because we have to take then larger sample and for the test. Well, so regarding this two sample means, again if either of these two sample, the sample size is less than 30, then this should be considered as a small sample, and this small sample, as we have seen in this single mean also, it follows a t distribution. So here the statistics is your x1 bar minus x2 bar minus delta, and this hat sigma hat x1 bar minus x2 hat is the estimate of this difference between two mean, the standard deviation. So which is this test statistics is a random variable having a t distribution with n1 plus n2 minus 2 degrees of freedom, and this estimate for the standard deviation is a square root of an estimate of this one. So this variance is sigma 1 square by n1 plus sigma 2 square n2, like this. So if this population variance is known, and if it is not known, then it should be estimated by the pooled estimator. It is called the pooled standard deviation, or we square this pooled variance, SP square, which is we will get from this one. So x1 minus x1 bar square plus the summation of x2 minus x2 bar square divided by n1 plus n2 by 2, which is basically that n1 minus 1 times of this standard variance of this first sample, and n2 minus 1 times the variance of second sample divided by n1 plus n2 by 2, where these two quantity are the sum of the square deviation from the mean of the respective samples. So if we substitute the estimate of the sigma square in the expression of this variance, then we get that this t is equals to x1 bar minus x2 bar minus delta divided by sp multiplied by square root 1 by n1 plus 1 by n2, which is a random variable having t distribution with n1 plus n2 minus 2 degrees of freedom, and this sp can be obtained as this sp square equals to n1 minus 1 into s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. And the critical regions are this for that statistics for this left sided test, that is whether the mu1 is less than mu2, then t whether the t is less than minus t alpha, in this case t is greater than t alpha, and two sided test whether t is less than minus t alpha by 2 or t is greater than plus t alpha by 2. So, we will take one problem on this small sample test is like this, that the random sample readings of the concentration of the pollutant in the water at two locations A and B are as follows. So, there are two locations, one is that location A and other one is this location B, and there are for this location A we are having 5 samples, and for this location B we are having 6 samples. So, this problem is taken because you see that in it is not required that we should have the same length of this data. So, that n1 and n2 need not be same. So, for the sample 1 we are having 5 samples, and for the sample 2 we are having 6 samples. So, use the 0.01 level of significance to test whether the difference between the means of the concentration at two locations is significant or not. So, then what we have to do? We have to first if we formulate that hypothesis, then the null hypothesis is that it is the whether the difference is significant or not. So, this is a two sided test, and the null hypothesis we put that mu1 minus mu2 is equals to 0, because we are trying to test whether these are different or not. So, mu1 minus mu2 is not equal to 0, that is what our test goal. So, this we have put in this alternative hypothesis, and this this mu1 minus mu2 equals to 0 is your null hypothesis, and here the level of significance alpha is your 0.01. The criteria for rejection of the null hypothesis is that if the t is less than minus 3.25 or t is greater than greater than 3.255. So, these two values are basically the statistics value at the significance level 0.01, and for the t distribution having the degrees of freedom equals to this sample length. Say this is your 5, this is your 6. So, 5 plus 6 equals to 11 minus 2. So, 9. So, with the degrees of freedom 9 at significance level 0.01 we get these two values, that 3.25 and minus 3.25 and 3.25. So, if our test statistics is falling in this region, then we should reject the null hypothesis. And the statistics that we know is that x1 bar minus x2 bar minus delta divided by sp square root of 1 by n1 plus 1 by n2. So, this x1 bar is a sample mean for the first sample, x2 bar is a sample mean for this second sample, that we can get whatever the data that we are having, and this sp, that is a spooled variance spooled standard deviation, we should also calculate whatever we have discussed so far. So, here are the calculations. This x1 bar, which is the mean for the first sample, which is 8.23, and mean for the second sample is your 7.94. Variance for this first sample is 0.01575 and variance for the second sample is 0.01092. So, these sample estimates we have already learned. So, you can we can apply that one for whatever the data is given, and we will get these sample estimates. Now, this pooled variance is that n1 minus 1 times this standard deviation of this first sample, the variance of the first sample multiplied by plus that n2 minus 1 times of this variance of second sample divided by n1 plus n2 minus 2. So, we will just use this one. So, this first sample is, that there are 5 samples. So, it is 4 multiplied by its variance, and then the second sample size is 6. So, 6 minus 1 5 times its variance divided by 5 plus 6 minus 2, which is 9. So, we will get that 0.01306. So, the SP here is equals to your 0.1143. Hence, the T is equal to x1 bar minus x2 bar minus delta divided by SP square root of 1 by n1 plus 1 by n2. So, if we put this one, we will get the statistics as 4.19. Now, this 4.19, which is greater than your 3.25, it is falling in this right side of that distribution, and which is obviously greater than the critical value. So, the null hypothesis must be rejected at this 0.01 level of significance. So, we can say, so in this null hypothesis you can say that it was there that both the sample means are same. So, we must reject this null hypothesis. That means, we can infer that the mean from both the locations are not same. Well, so so far we have seen that what is the test for the that one mean and two means, and now we will see that the variance. First we will start with this one variance, and then we will go for the second variance. And let us consider a sample size n drawn from a normal population with variance sigma square, and this null hypothesis is h naught equals to sigma square is equals to sigma naught square, and the alternative hypothesis is h1 can be say that less than sigma 2 square, this is greater than sigma naught square, and this is not equal to sigma 2 square. So, anything this can happen. So, and depending on this null hypothesis also will change. So, this is basically for this alternative hypothesis when this is not equal to this. And in our last lecture, when we are doing this sampling distribution, also we have seen that this variance, that is n minus 1, where n is the sample size, that times that variance divided by sigma naught square, this ratio is basically following a chi-square distribution. So, this chi-square, so these statistics we can use to test for this single sample variance. So, this is the one variance, and the sigma naught is your some threshold value for this which we are inferring from this population, and this quantity, this statistics is following that which is having a chi-square distribution with n minus 1 degrees of freedom. Now, the critical region for testing this one sample variance, and of course, here the assumption is that this population from where the sample is drawn is having a normal distribution at the significance level alpha. If it is the one-sided test and this is if it is a left-sided test, then whether the chi-square, the statistics that we have discussed so far, that is n minus 1 time variance divided by sample variance divided by this population variance, that statistics, if it is less than this chi-square value at the 1 minus alpha cumulative distribution, if it is less than that, then we should reject the null hypothesis. And if it is for this right side test, if it is greater than that chi-square alpha, chi-square alpha, then we reject this null hypothesis. And for the two-sided test, if it is less than 1 minus chi-square 1 minus alpha by 2 or greater than chi-square alpha by 2, then we should reject this null hypothesis. If we just see quickly that you know that this typical shape of one chi-square distribution, it looks like this. So, this is not symmetrical. So, here what we are referring to, that this left side. So, this area is basically what we are telling. So, this value is what we are referring to as this chi-square 1 minus alpha, and the same area for this, that when we are doing for this right hand side test, suppose that this is your this area, if is your what is that alpha, then this value what we are saying that is a chi-square alpha. So, here the chi-square 1 minus alpha means the total area below this curve is 1. So, this full area, apart from this red one, this starting from the white area as well as this shaded area is your 1 minus alpha, and these are for this one-sided test. Now, at this significance level of this alpha, if we go for this two-sided test, then obviously we are testing that 1 minus alpha by 2, which is obviously will be little smaller than this one. So, this one and this will be somewhat greater than here. So, these two value, which is your chi-square 1 minus alpha by 2 and this is your chi-square alpha by 2. Okay. And this area, this now what I am setting, that blue area here plus the blue area here should consist, it should be equals to alpha. And as this chi-square distribution is not symmetrical, so here these two values that we are looking for this critical value will not be symmetrical, as we have seen so far in case of that standard normal distribution and as well as in the t distribution. So, these are the critical regions for those, for the one sample for the chi-square distribution for one sample variance. We will take one example here. The maximum permitted population standard deviation sigma naught in the strength of a concrete cube is 5 kilonewton per meter square. So, if this is our requirement, use that 0.05 level of significance to test whether the population standard deviation is greater than this threshold value, that is 5 kilonewton per meter square, if the strength of 15 randomly selected concrete cubes cured under a certain process have a standard deviation equals to 6.4 kilonewton per meter square. So, we have taken randomly 15 samples and that sample standard deviation is 6.4. So, if we just compare this 6.4 and 5 kilonewton per meter square, this is obviously greater than that. Now, through this hypothesis testing for this variance, one variance test, we have to say that whether probabilistically we have to infer whether this value is really greater than what is our requirement. So, our null hypothesis is that whether this sigma is less than equals to this 5 kilonewton per meter square, because we are targeting to test whether this that population standard deviation from which the sample is taken is really greater than 5 kilonewton per meter square or not. So, the level of significance here is that 0.05. The criteria for rejection of this null hypothesis is this chi-square is greater than 23.685. Now, where from we got this 23.685 is the value for the alpha 0.055, where this chi-square distribution having a degrees of freedom equals to 15 minus 1 equals to 14. So, now if we see that, if I say here that this is your the chi-square distribution with 14 degrees of freedom, then that this chi-square alpha, that we are saying that if we just say that this red area is your 0.05, then this value is your 23.685, which you can get from any standard textbook. These tables are, these chi-square tables are given here. So, if my test statistics falls in this one, you know that this is your critical zone. So, if the test statistics fall in this zone, then we have to reject the null hypothesis, and if it is below this one, so we cannot reject the null hypothesis with the sample data that is available with us. So, this is why this 23.685 is our critical value, and if we do this, if we calculate this test statistics, then with this sample data, it is now n equals to 15 minus 1 and 6.4 and divided by this 5 square, then we get the 22.94, which is definitely less than that our critical value. So, null hypothesis cannot be rejected at 0.05 level of significance. That means, we cannot say that whatever the sample data that we are having, from that we cannot infer that the population standard deviation is greater than our what is our target, that is what is our requirement 5 km per meter square. It is not greater than that, even though we have seen that numerically the sample standard deviation is something 6.4, which is clearly greater than this 5, but probabilistically we cannot infer that. Well, now we will take that hypothesis concerning two variances. Let us consider two sample size of n1 and n2 drawn from two normal populations. So, this is that requirement, that when whatever sample we are drawing, it is from the normal population with their variances sigma 1 square and sigma 2 square. So, here the null hypothesis is can be like this. So, sigma 1 square is equals to whether they are equal to, or 1 is less than, or 1 is less than other, like that. So, here the state statistics are depending on the what is your alternative hypothesis, whether the sigma 1 square is less than sigma 2 square, or sigma 1 square is greater than sigma 2 square, or they are not equal. Depending on that, the state statistics is S2 square by S1 square, or f S1 square by S2 square, or f is equal to Sm square by S small m square, where the numerator is the larger sample variance. So, you see for the first case, when we are saying that the sigma 1 testing, we are trying to test that whether sigma 1 square is less than sigma 2 square, then we have to test that the sample variance for the second sample divided by sample variance of this first sample. These statistics we should use. On the other hand, we should use that sigma the variance for the first sample divided by variance for the second sample, if the first sample is greater than the second one. And if we are testing the two-sided one, then we have to find out which one is greater. So, that greater value should be in the numerator, and this f is having a f distribution with n minus 1 and n minus 2. So, this is basically that this n when we are writing here, this is there is something typing mistake here. So, this the first one is for the numerator. So, whatever in the statistics, whatever is there in the numerator, that should be your first degrees of freedom, and whatever is there in the denominator, that should be your second degrees of freedom. Now, if I just want to take all this thing in a single statement, then whatever we are testing, we always the f statistics that we are calculating, it should be always, we have to keep in mind that that should be always greater than 1. That means, in the numerator always we are putting the greater value, and this numerator and the denominator we are putting the smaller value. So, if we can ensure that, then we can say that that f statistics is having a f distribution which is following the f distribution with the first degrees of freedom is the larger sample size minus 1, and second degrees of freedom is the smaller sample size minus 1. This is not 2, this is also 1. So, these 2 degrees of freedom with that is a f distribution. So, here so there are again the 3 different cases, and there are 3 different test statistics, and we are if we are just taking in this way, whether with the first one is less than the second one, or first one is greater than the second one, or they are not equal, then here you can depending on that you have to find out what is your critical region here. And on the other hand, if you just want to just what I just now mentioned, that if you just simply want to use that which one is your larger variance, which one is your smaller variance, then always for all these cases you can calculate this f statistics, which is following that f distribution having this n minus 1 degrees of first degrees of freedom, and second degrees of freedom is n small m minus 1, where n capital subscript capital M is the larger sample size and n subscript small m is the smaller sample size. We will take up one example here. It is proposed to determine whether there is less variability in the strength of concrete cubes cured under process 1 than those cured under process 2. So, there are 2 different processes identified, and we have to test whether the strength of concrete in one process is different from the other process, or here we are testing that whether in this process 1 what we are getting is the strength is less than this process 2, before I can declare that okay, we should follow the process 2 for the curing the concrete, so that we can achieve that greater strength. And so, sample data is taken. So, like that there are 12 randomly selected cubes are there under 2 processes are tested. It is found that this S1 is 3.5 kilonewton per meter square and S2 is 6.2 kilonewton per meter square, and test the null hypothesis whether they are same against that alternative hypothesis, whether the first one is lesser than the second one at the level of significance 0.05. Here the null hypothesis is this, and alternative hypothesis whether the sigma 1 is less than sigma 2 square, level of significance is 0.05. So, and this criteria for rejection of this null hypothesis whether if the statistics is greater than 2.42. So, how we are getting this one? So, this is the f distribution having the degrees of freedom of the sample size, that is in both the cases the sample size is 12 here. So, 12 minus 1, so 11, first degrees of freedom is 11, second degrees of freedom is also 11. So, where this S as f is equals to S2 square by S1, S2 square by S1 square, and you have seen that this S2 is your 6.2 and S1 is 3.5. So, S2 is greater than that. So, if we use this test statistics, the S2 square by S1 square. So, it is but anyway here in this case both the sample sizes are same. So, here the test statistics comes to be 3.14, as this 3.14 is greater than 2.82. So, the null hypothesis must be rejected at 0.05 level of significance. Okay, so far in this hypothesis testing, what we have seen that we have first found out in the earlier lecture what are the sampling distribution of those that estimated value, the sample estimation, and in this hypothesis testing we are basically trying to infer something about the population from which the sample is drawn. Suppose that we are having this some sample of size n, and we estimate what is its mean, and if we want to infer something from that sample estimate and we want to infer something regarding the population, then we have seen that we have tested for this single mean, we have tested for the 2 means, and again we have taken the single variance, we have taken the two variances. Like this we can test, and there are several, we have even used different examples from this civil engineering. There could be some many examples like this, where you can use this theory to infer something about their population, because always the sample that we get is limited. So before we can infer something about their population, we have to use this test properly, so that we can judge something. Even though we get some numerical values from the sample, which just by this comparison of this numerical value can show you something else, but whether that is really significant, because always you take one sample and take the another sample from the same population, the statistics may not be same, the mean for both the samples may not be exactly same. So those differences, whether they are really significant from the statistical point of view or not, to test that one, whatever the discussion we have done so far with respect to the single mean, two means, single variance, two variances that we have to follow. Now we will take some time to spend on that, because you have seen that in many times I have mentioned that okay, this data is following that distribution. So now we are having the data. Now with that data, how can we say that, yes, this data is coming from a population which is following this distribution. So there are basically two things. One is that first we will do some graphical approach, and there are some statistical tests also for this, to infer that whether this is really following that population from which the sample is drawn is really following a particular distribution or not. So we will start that one, and the first thing is the graphical representation, which is maybe which we generally test through this probability paper. So the construction of this probability paper and the testing, that how whether it is really following or not graphically, that we will see now. So the empirical determination of the probability distribution of a random variable. So in many real life scenarios, the actual probability distribution of a random process is unknown. So on the basis of the frequency distribution of the sample data that we are having, so determined from this observed data, which is the sample available to us, some probability distribution may be assumed empirically. Probability papers are useful to check the assumption of a particular probability distribution of a random variable. Say that I have a sample, I am saying that okay, this sample is taken from a population which is distributed normally. Now we have to use a normal probability paper and plot that data, and then we will just discuss how we can infer that or the visually how we can inspect that whether it is really following the normal distribution or not. And again we will take some statistical test to probabilistically infer whether really that is following the distribution or not. So a probability paper is a specially constructed plotting paper where the one of the axes where the random variable is plotted is an arithmetic axis, and the probability axis is distorted in such a way that the cumulative probability distribution of the random variable plots appears as a straight line. So there will be one word appears as a straight line. So for the CDF, that cumulative distribution function of different probability distribution, to plot as a straight line, separate probability papers are needed. So if I want to test that whether it is following a normal distribution, then I have to use a normal probability paper, and if I want to test whether it is following a exponential distribution, so we have to use the different paper. So now how these papers are constructed and how it is tested, we will see now. So first we are taking this normal probability paper, which is most widely used to test that whether the sample data belongs to a population which is normally distributed. So this normal probability paper is constructed on the basis of standard normal probability distribution function. The random variable x is represented on the horizontal, or sometime in some cases vertical axis also, but mostly this random variable is generally represented on the in the horizontal axis, and that axis is a arithmetic scale. The vertical axis or horizontal, if I just reverse this one, as I was telling that if this x is on the vertical, then this one will be the horizontal, otherwise in most of the cases it is vertical axis. So, the vertical axis represents the two scales, the standard normal variate z equals to x minus mu by sigma and the cumulative probability values f x ranging from 0 to 1. Now, before I go further, if I just see it graphically how these things, how the concept is taken, you know that in this if this is your that x, this is the axis for your the random variable, and if this is your that cumulative probability axis, which is that fx for this specific value x, which is a cumulative distribution. You have seen earlier towards the beginning of this course, this distribution is generally looks like this. So, which is asymptotic to 0 at this minus infinity, and which is asymptotic to 1 at plus infinity. And we have also seen that it is from this, if it is a standard normal distribution, then it is from this minus 3 to plus 3, almost that most of this probability is exhausted here. Now, if I just take that this is your, say that for this normal standard normal distribution, if we just see, so here the mean is coming approximately say 0, and this is say minus 3, and this is say something plus 3. Or in some computer applications, sometimes even we can go that minus 5 to plus 5, almost very close to 1 probability is exhausted there. So, what we generally want to do is that basically whatever the sample data that we are having. Now, if I just plot, now you know that this is also that arithmetic scale, and this is also the arithmetic scale. Now, if we plot the data, whatever the data that we are having with respect to their cumulative probability, how do we get the cumulative probability we will discuss. So, if we can plot that one, and if it follow approximately this line, then we can infer that yet it is following this particular distribution. But by that eye inspection, it is very difficult to say whether this particular shape is following or not. Rather, we can say if we can distort this axis in such a way that this will appear as a straight line, then inspecting by eye that whether this is following a straight line or not, that is easier than comparing that whether it is following this particular curvilinear path or not. So, to make this axis distorted, what we generally do is that we generally take a straight line between this, and now we let us create one new axis here, such that suppose that this I am starting from point 25. So, I am starting from this line going up to this point, and then I am going to this straight line, and from this one I am just giving the name, giving the number as 0.25. Similarly, suppose that I am starting from the 0.75 here, I will go to this one first, come to this straight line and go here, so that I will write that 0.75. Similarly, from 0.05, 0.1, 0.15, like this, all these points whatever is there, if I just go there and just distort this axis, basically this axis I am just squeezing some part, expanding some part in such a way that this red curvilinear path is stretching to a straight line. And after in that axis, in that distorted axis, if I plot whatever the data that we are having, that if it appears that straight line, then we can conclude that it is following the normal distribution. Now, with this x axis keeping in the same axis and this distorted probability axis, whatever the paper that we get, that is known as this probability paper. Now, this example that I have shown, this is for the normal distribution, and this similarly this can be done for these other distributions as well. Now, second question is how we will get what is their cumulative probability. For that, there are different plotting positions formula is available. For example, the California gave that m by n, Hazen gave that 2m minus 1 by 2n. We will give the formula m by n plus 1, where this n is the total number of observations, that is the sample size, and m is the rank of the data point when the observed values are arranged in ascending order. So, this plotting, from this plotting position, generally this Weibull plotting position is mostly used. Using this one, we get this cumulative probability distribution, and we get their that probability value, and if then we will plot it on these different probability papers. We can first plot it on this normal probability paper and check whether it is coming to with a straight line or not, and other probability papers also. On what it is following this straight line, we should conclude that yes, the population of this sample is following that particular distribution. We will take one example here. the observed strength of 30 concrete cubes is given below, means in this table. Next slide. Check whether the strength of the concrete cube follows the normal distribution or not by plotting on this normal probability paper. So, these are the strengths of this 30 samples are given here, and after doing this using that we will formula for their plotting position, we get all those, we just arrange it in this ascending order and get their respective values, and then we plot it here. Now, you see here this x axis is your that actual strength. The pictorial representation that I have given, it is for this standard normal distribution. Now, this axis can easily be for this any axis that you know, and so here that this actual axis is shown. So, what is the strength range, and this you can see that this axis is now distorted to get that what is their probability values. Now, this one is coming, this blue plus sign are this the data, and now you have to, by your judgment, you have to test whether these blue lines are your that this blue plus dots are really following a straight line or not. So, this is just by your eye inspection, and there are some tests also, statistical tests, that also we will see next. And this so this is for this normal probability paper, and the general probability paper and the probability plot. The random variable x is represented on the horizontal axis in the arithmetic scale. The vertical axis represents the probability distribution in such a way that if it follows a particular distribution for which the probability paper is prepared, whether the probability paper is prepared for the normal distribution or gamma distribution or exponential distribution, depending on that, if it appears on that paper as a straight line, then we can say that this is following that particular distribution. Thus, if the plotted data points gives rise to the straight line on the paper, then the data points belongs to the particular probability distribution for which the paper is constructed. So, now if I so this is for this general case. Now, say that so this cumulative distribution that I have shown it here, this is, you know, that this is for this normal distribution. Now, I can take for this exponential distribution, and this exponential distribution also. So, you know that that will be, if I just take, so this exponential distribution, the cumulative distribution looks like this, that you know. So, now this one also, where this almost is approximately almost equals to 1. So, from there if you have to draw a straight line, and then you have to this probability axis you have to distort, thus using the same method as I have discussed now. So, whatever the new axis you will get with respect to this actual axis, this horizontal axis of this random variable, you will get the paper which is for this exponential distribution, and on that paper if it appears to be the straight line, then we can say that this is following the exponential distribution. Now, one thing may ask that, now again I am going back to the problem that we have discussed, that now this blue stars, whether this is really a straight line or not. So, this is now whether you can say just by your eye inspection you can say that whether it is really following the straight line or not. So, that is your basically a personal judgment, that whether yes, I can say that it is following a straight line, or sometimes we can say that no, it is not following the straight line like that. So, what we need actually, we need one such one probabilistic test also, for which basically we can say, we can infer probabilistically, yes, with at this significance level this particular data sample or data sample from the population of that data sample is following that distribution. So, there also we need the hypothesis testing. There are different test statistics are there, different tests are there, the chi-square test, Kolmogorov-Smirnov test. Through that test we can infer that which distribution that the population is following, and that we will take up in our next lecture. Thank you.